We have Travis Butz with Burgess and Niple and Dan Gorley with ITD, and they're going to be presenting on the Perrine Bridge Asset Management Plan and repairs.
All right, thanks everybody. I'm Travis, this is Dan. So I'm with Burgess and Niple, Dan's with Idaho Transportation Department. And we're going to talk about the IB Perrine Bridge Asset Management Plan, which being in performed for ITD. I'm going to give a brief overview of the bridge itself. Then I'm going to hand it over to Dan. He's going to talk about what ITD is looking for in an asset management plan and how they use them. And then I'm going to give some details about what we did for the Perrine. So the Perrine Bridge is in Twin Falls, which is about 2 hours southeast of Boise. It's over the Snake River Canyon. It is a weathering steel arch truss bridge. It opened in 1976. The overall length is 1,500 feet with a main span of about 1,000 feet. And it is 486 feet over the Snake River below. So it's a pretty impressive span if you get a chance to go see it sometime. One important thing I wanted to point out that's not necessarily related to asset management is that immediately to the east of the bridge, Evel Knievel attempted to jump over the Snake River Canyon on a rocket motorcycle in 1974. So I don't have time to discuss that in detail in this presentation, but you might want to look that up on YouTube. And with that, I'm going to hand it over to Dan to talk.
Thank you, Travis. They come from all over the world to jump off of this bridge. It's pretty amazing that they parachute. So if you're working on the bridge and you're climbing the arch and all of a sudden, boom, here comes somebody jumping by you. It's quite the experience. But anyway, for ITD to assess the long-term needs of ITD's largest bridge structures, within the next 20 years, several of them will need major rehabilitation, which will create an enormously high cost for ITD. And ITD's developed 8 individual bridge asset management plans so far for high-cost replacement bridges in ITD's inventory. These efforts help ITD to analyze future funding scenarios and investment trade-offs to ultimately pay for these expensive assets. Basically, this is one of our ways of communicating with the public. This rolls up in our Transportation Asset Management Plan. So the Bridge Asset Management Plan rolls up into the Transportation Asset Management Plan. So when we're doing our deterioration on the system, it's global of everything. We got the history of our bridges. We go in and set parameters that match the history of our bridges. So all bridges are deteriorated based off MBI and element data, including the long-term history. And this has to do with the performance measures, percent good and percent poor, how much is coming on, how much is going off based on the funding you're using. So the budgetary distribution is prioritized on the goals. So with this bridge asset management plan, it's an individual bridge deterioration. So it's kind of like a refinement to our model. It's a specific bridge focus. It's all inclusive. It provides the basis for risk-based decisions and individual bridge deterioration with specific life cycle cost actions are hard-coded into our models. Diving in just a little bit into life cycle cost analysis and BRM, Ashtaware BRM, we take this asset management plan that Burgess and Niple provided for us on the Perrine Bridge, and we put it into our Ashtaware. We code all these actions into the just for this bridge into the system, and these are the actions that are coded, and then it produces a deterioration curve. And so the do nothing curve versus if we follow this plan, this the lighter blue line is following the asset management plan for the bridge asset management plan for the Perrine. This MBRM, it actually shows the effects of project recommendations on selected elements in a given year. So the graph shown on the right is for a specific element, and then all these different elements will have these type of effects on the deterioration based on the actions taken. So I think we've come a long ways with the Ashtaware over the years, and this is the first time we've been able to do this in Idaho. We freeze these life cycle plans to the program scenarios to account for them in the network optimization. So when we're doing different scenarios, putting different funding in, these are fixed actions in the program and projects. Obviously we can change them if we need to, but they are fixed in the system. So all the scenarios include these actions on this bridge. So the key benefits of creating life cycle plans and phrasing them to the program scenarios in BRM is account for bridge deck area and bridge condition performance measures, ensure no additional projects are recommended by VRM models in the program optimizations, and account for benefits of recommended projects in the recommended project years. I'll turn this back over to Travis.
All right, thanks, Dan. So what's on the screen here are the components of the asset management plan we put together, and these were laid out for us by ITD, but I'm going to step through these different pieces that we put together into the final plan. So the pieces are the data sufficiency memorandum, the bridge condition assessment, a risk register, an alternatives analysis matrix, and a maintenance and monitoring manual. So the data sufficiency memorandum is a collection of existing documents about the history of the bridge. So the original plans, plans for rehabilitations, shop drawings, load ratings, inspection reports, and anything else we can gather as far as what's been done to the bridge over its life. We collect that information and then we tabulate it in different forms that can be used by ITD or the owner of the bridge for future management. So a couple of examples of things that showed up in the report are on the slide. On the left is a timeline for the life of the bridge, so it tells the date of the original design, the date of it opened to traffic, and then the dates of subsequent rehabilitations and repairs to the bridge and what was done in those years. And then on the right is that is a list of elements on the bridge that are A514 or T1 steel, so that's a hot topic of late. So there are some plates. They're mostly in non-critical areas on the bridge, but we did go through and locate all those plates and include a list of that in this report. The second document is the bridge condition assessment, and this was not a full inspection of the bridge, but what we did was review past inspections of the bridge and note previous deficiencies that had been identified in those inspections. And we took a look at those areas and then other areas that commonly require maintenance, like the joints and the bearings, places we expected that money would need to be spent in the coming years, and documented those areas. And we also did some chloride concentration sampling, so samples in the deck and the abutments to look at chloride levels, just to anticipate future needs for patching and repairs in those areas. And that's tabulated at the bottom of the slide, a summary of what we found. And we did find some minor contamination in areas of the deck, and then a few areas in the abutments where it was more concentrated, mainly in areas where there had been leakage on the back wall, and that affected some recommendations we would make later. The next step was the risk register, and this takes the form of a list of risks the bridge might encounter over its lifespan, as far as shortened life or major repairs that would be necessary. And what mostly fed into this report was a workshop we had with stakeholders for the bridge, which were mainly people at ITD responsible for the management and maintenance of the bridge, and then some people at BNN who have experience with this bridge type and had some expertise in things that might be encountered over the life of the bridge. So for the workshop, prior to the workshop, we sent out a questionnaire to all the participants, and they put together a list of things that they thought might be risk factors for the bridge over its life. And we asked them to quantify the likelihood of occurrence over the life of the bridge, and then also identify any potential mitigation options. So when we got together in the workshop, we went through that list. We discussed those different risk items in detail, and we tried to put a number on the associated cost with mitigation, and also refine our likelihood and options for mitigation of those different factors. So a sample of what was in the final product is down at the bottom of the slide. So we had a list of risks that we identified, and then a description of the conclusions that went along with that. So the top of the list there is the T1 steel, the A514, and how we thought that might impact the future life of the bridge. Next component is the alternatives analysis. So in this report, we identified alternatives for the maintenance and rehabilitation of the bridge in the future, and we looked at cost outlays for each of those alternatives, and we presented the results of that in a decision matrix, which is like a life cycle cost for the future life of the bridge. Also, as part of this report, we we looked at future bridge replacement alternatives for the bridge, and there are no plans to replace the bridge in the near or even intermediate future. It's far off, but just for the purpose of comparison to maintenance costs and for a total picture of life cycle cost of the bridge, we put those costs together as well. So the slide here at the bottom is, this is a table of rehabilitation options and costs for different components to the bridge. So you can see we went through the deck, the joints, the wearing surface, and this is just the beginning of a very long list of things that might need to be done to the bridge in the future without specific dates associated with them. And then the next slide shows the part of the decision matrix we ultimately assembled. So what you're seeing here is a comparison of alternatives for maintenance of the deck. So this takes the form of a life cycle analysis, and it goes out to the 100-year life of the bridge, which is about 2075. And we looked at the top half of that table is looking at, if we maintain the existing deck on the bridge, the original deck, for the entire 100-year life, what do we anticipate the associated costs are? So that's got more frequent and more expensive overlays associated with it, and more maintenance in general to make sure that that deck stays intact. And then an alternative where we looked at assuming we need a deck replacement in the future with less aggressive maintenance associated with it. And maintaining the existing deck, as you might not be surprised, is the winner in that comparison, but we put together those costs for any future developments where comparisons are necessary. The final piece is the maintenance and monitoring manual. And the purpose of this manual is to identify critical areas for future inspection and monitoring on the bridge. And it includes recommendations for schedules for inspection and maintenance on the bridge. And it includes a log, a maintenance log, so that inspectors can note changing conditions and any repairs that they are recommending or that have occurred on these different components. So the example over on the right, this is what we're looking at in the picture is an access manhole that goes down through the deck to get to the catwalks below. You can see there are stay-in-place forms around those manholes that are rusty. In the report, we're identifying that as a problem. We say what we think is causing the problem, and we recommend what future monitoring we think is necessary and how to access that area. And then the bottom portion is the maintenance log we provided, which is basically a note sheet for the inspector to say, here's what I'm finding with my periodic inspection, and then this is any additional repairs I think need to be performed on this item. So once we have all those different pieces compiled, we assemble them into the asset management plan, the final report. So this is just a combined document with all those pieces together. And we have a front end on that document that provides an executive summary of the content of all those reports, and then an overall rehabilitation, maintenance, and replacement recommendation section in the front of that report. And then those 5 components appear as appendices, and then that becomes a big, thick document for Dan and ITD staff to go through when they're processing that information, as he described. The AMP led into a repair project due to some of the recommendations that we made. We did the plans for that repair project over the past year or so. It's going to go into construction next year. I'm going to give just a brief overview of what's being done there and talk about a couple of interesting things that were deficiencies that we're going to repair. So the big item is the arch end post. So what you're seeing in the picture, that's BNN out inspecting the arch end post. So that is what right down below is the bearing point of the arch span, and that's the end column of the arch. So the upper and lower chord of the arch truss are tying in right there to the end post. And that vertical post, it's a box section with only a few access points, and access is a problem. That's part of the difficulty of dealing with this area, but I'm going to talk in a little more detail about that on the next couple of slides. Some other things we're fixing, we're doing some painting of corrosion-prone areas. One of them is the interior of that end post, and then also up at some joints and some places that were getting wet under the deck. We're repairing some items in the inspection access system, mainly cables and handrails. We're doing some patching to the substructures, so some of the areas of the abutment we noted earlier, and also pedestals for the bent supports. There are utility conduits under the deck on the bridge that require some repairs. The joints for the sidewalk needed some maintenance, and also the pedestrian railing had some minor repairs required. So on the end posts, what you're looking at on the left is an elevation of the end of the arch truss from the plans, and then that end vertical is the end post. And you can see where the upper cord ties into the end post, there's a gusset plate there. And the photo on the right is looking down into that gusset plate. So what happened there is you can see debris has collected, and that's just from water rolling down the upper cord, and debris collected in that gusset. And there are drain holes in the gusset, but they got clogged from the collection of debris. And you can see right here is a gap in the plate of the end post, and that was not in the original plans. That was from the erection of the bridge. The erector used a pin at that location to simplify the erection of the end post. That was later, it was only in service during erection, and then it got bolted permanently into place after erection. So it's no longer, it's still there, but it's no longer functional. But what it did was create a gap in the plate. So when water collected, because the drain holes were clogged, water poured down into the end posts and got the inside of the end post wet for some period of time. And what that resulted in was corrosion inside the end posts. And this is an old picture. The worst of these, the corroded bolts have already been repaired. So this has been repaired and load rated, and it is safe in its current condition. But as part of our project, we're going to go back and replace all of the bolts that have any corrosion on them in the end posts to restore it to near original condition. And then we're also going to divert the water with a drip bar on the upper cord to prevent water from collecting there, and also seal up that gap in the end post to prevent penetration. We're also going to recoat the inside of the end posts. As I mentioned earlier, access to the end post is very difficult. So you can see we have a rendering of the end post there on the left, and with the access panels removed, it's too small for a painter to get in there and work. So what we're proposing for the recoating is to use mechanical equipment that's used on pipes for coating the inside of pipes. So we can get into those access panel and then lower down this machinery that can blast and then coat the internal surface of the end post. And we can also use cameras to get in and inspect the surface finish and the profile of the coating once it's complete. So with that, I can take any questions. Thanks everybody for attending.
So you said that one of the repairs that you're doing for that bridge is that you're painting it. Is that
only in isolated locations?
Is that galvanized paint? No,
it's where we're painting under the joints, where there are wet conditions. It's going to be a three-coat paint, standard three-coat paint system with zinc primer, and then for the inside of the end posts, it's a two-coat epoxy flake system.
On one of the slides, you mentioned that the access system. The access system, was that built with the bridge, or was that retrofitted later?
Inspection access. Inspection
the
access
cables and stuff.
Yeah, that's a fancy word for some handrails that help you get down the arches. So yes, it's original to the bridge. So it's just there's grating on top of the upper cord to make it easier to walk on, and then handrails, or in some cases bars, to tie off to and put your hands on as you walk down, and then some catwalks to get down the end posts at the end. Thanks, everybody.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.